Today's an exciting day. You're going to prove the fundamental theorem of arithmetic.
Well, whoop-de-doo.
Exactly why is that supposed to be exciting?
It sounds pretty exciting to me.
Only because you're locked in a time warp with nothing to do.
It's a good question, so let me answer in two ways. First, from a mathematical point of view, the theorem explains how the natural numbers are built. Imagine each natural number as a padlock. The fundamental theorem tells us that each of these is unlocked by a unique key, namely its prime factorization. By studying the proof, you'll better understand the relationship between the keys and locks. Second, it's exciting that your mathematical powers have reached the level where a proof of the theorem is possible. Most students don't even see a proof until they're at college, let alone try to build one themselves, which is exactly what I expect you to do.
Just one more superpower to add to my arsenal.
Let's start by stating the theorem. Who can do that for me?
So n is a natural number greater than 1. So n may be a prime number. If it isn't, then it's the product of prime factors lined up from smallest to biggest.
Right. We line up its prime factors in non-decreasing order to produce its unique prime factorization. This theorem is of a very useful type called a unique existence theorem. It tells us that something exists and that there is no other like it.
Just like me.
The existence part tells us that a prime factorization exists. And the uniqueness tells us that it is the only prime factorization.
So we have to prove existence and uniqueness separately?
Yes. In fact, we'll start by proving existence as follows. I want you to prove a statement that is almost the existence that we want. In proving existence, we want to show that a natural number n greater than 1 is a prime or the product of primes. But instead, you're to prove this.
But that says if n is greater than 1, then it's true for numbers from 2 to n. But we're only interested in that if it's true for n.
Right. So why make it more complicated than it is?
Good question. Why do you think?
Maybe because you're going to do it by inductionization?
Proof by induction.
That's right. We're going to use induction, and proving this stronger statement will actually make it easier. For convenience, we'll give this statement the name P sub k. Who's going to lead the proof?
I'll
Me,
try.
me! You start, and I'll finish.
Okay, so we proceed by induction. So the base will be p sub 2.
Correct.
We have to show that if 2 is a natural number greater than 1, then every number from 2 to 2 is either prime or a product of primes.
2's prime, so that's obviously true.
Am I doing this proof, or do you want to do it?
Carry on, you're doing well enough.
Like Ron says, it's trivial.
Now the induction step?
So take a natural number, m, greater than 1, and suppose every number 2 through m is prime, or a product of primes.
Good. So the induction hypothesis is P sub m.
What is it we have to prove next?
I think we have to show that if it's true for m, then it's true for m plus 1.
Okay, so if you take m plus 1, so we have to show that every number from 2 to m plus 1 is either prime or a product of primes. I don't know how to do that.
We know that everything from 2 to m is a prime or a product.
From the induction hypothesis.
So that just leaves m plus 1 itself. We have to show that it's either a prime or a product of primes.
Well, the first part's easy. If it's a prime, then everything's hunky-dory.
Because 2 to m are primes or products of primes, and m plus 1 is a prime, so everything from 2 to m plus 1 is a prime or product of primes.
So proceed by cases. Case 1. m plus 1 is prime. As you pointed out, by the induction hypothesis numbers from 2 to m are primes or products of primes. And so, if m plus 1 is also a prime, then you've proved it for m plus 1. So in this first case, p of m plus 1 holds. Continue.
So then if m plus 1 is not prime, I don't see where to go here.
We have to show it's the product of primes.
I don't know either. Ron, say something random that we know about m plus 1.
Well, okay. If you write m plus 1 and turn it upside down, it makes 1 plus w.
No, Ron, random but relevant.
Okay, it's not a prime number?
Okay, it's not a prime number.
So it has a factor.
So it has a factor other than 1 and itself.
So if x is the factor, then it also has a factor y, and x times y equals m plus 1.
Wait, so x and y are both greater than 1 and less than m plus 1, right? So I mean, they're both between 2 and m, so...
So the induction hypothesis says they're either primes or the product of primes. So
when you multiply them together, you get a bigger collection of primes.
And so m plus 1 is the product of primes.
Well done. Let me summarize your argument as follows. Since in this case, m plus 1 is not prime, then it has factors x and y. And these factors are not 1 and not m plus 1. And so, by an earlier exercise, they're between 2 and m. So by the induction hypothesis, x and y are both primes or the product of primes. That means that x times y is the product of primes. Then since x times y is m plus 1 is the product of a collection of primes. So you now have proved p of m plus 1 in both cases.
So then m plus 1 is either prime or the product of primes.
So all the numbers from 2 to m plus 1 are primes or products, which is what we were proving.
So yes, you've proved p sub m plus 1 hold in both cases, which means we finished the induction step. And, having already proved the base, your induction proof is complete. You have proved that, for all natural numbers n greater than 1, every number from 2 to n is either prime or is the product of a collection of primes. However, we're not quite done.
Oh, that's actually more than we need. So if n is greater than 1, then everything from 2 to n is a prime or a product. And n is certainly between 2 and n, so n is either a prime number or a product of primes.
Perfect. Now, please read over the proof, and when you're certain you understand each and every step, then we'll consider the second part of the proof, to show that the prime factorization of n is unique.